Alright, for this video I want to go over where the value 9.81 meters per second comes from, meters per second squared. And this is where we're going to bring together two equations that we've introduced previously. One equation is this force of gravity is equal to mass times the acceleration due to gravity. This was introduced when we wanted to solve for weight and also force of gravity. Another equation that we use to solve for force of gravity is the force of gravity is equal to the universal gravitational constant times one mass times another mass divided by the distance squared. When you look at these equations, they both solve for the force of gravity, but they look different. That's because this equation on the left is for any two objects, or one object being the Earth, and any other object. So this is specific to Earth and any other object, or specific to things on our Earth. This equation, though, is more general. It's for any two objects. So it can be the Earth and any object, but it can also be the Earth and the Sun, Saturn and Venus, Mars and Jupiter, our solar system and another solar system, a black hole and another galaxy. It can be between any two objects. What we do know, though, is that this equation on the left, when we use it, the g that we use and plug in is 9.81 meters per second squared. And this is the acceleration due to Earth's gravitational force. So if we want to say, and the purpose of this video is to find out where we get this 9.81 meters per second squared is, let's go ahead and try to isolate this variable, g, and divide m on both sides. We get f of g over m is equal to g. And we want to know where this g comes from for Earth's purposes. And if that's the case, one of the things that we can do is go ahead and bring what's on the right side of this equation over and plug it in to here. You see that if this is f of g is equal to g times m1 times m2 over d squared, we can fit that into there and do a little substitution. If we do a little substitution, we get big G times m1 times m2 over d squared, and that's all divided by m. One thing we can do now is actually get rid of an m. All we can say is that this m can either cancel out m1 or m2. It doesn't really matter as long as it cancels out one mass, because we are only concerned with the mass of the Earth in this case, and we're looking for Earth's acceleration. And if that's the case, we simplify to g times m over d squared, where this m is the mass of the Earth, and this d squared is the radius of Earth. And if that's the case, we also know that big G is the universal gravitational constant, and it never changes. So with all that, we can now plug in our values that we know. Little g is equal to 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared, times the mass of the Earth, which is about 5.98 times 10 to the 24th kilograms, so 4, and divide that by 6.37 times 10 to the 6th meters squared. So all of these values here are rounded, but if you plug this into your calculator, you should actually get a value that's close to 9.81, but it's actually 9.829 meters per second squared. And that's not exactly 9.81 because these numbers here are rounded.